In this note, we are going to further clarify how to set up partial fraction decomposition. On the input, we have the rational function n over d. In the decomposition, we have the parameters a, b, c, d, e, f, g. We want to show that the number of the parameters actually equals the degree of the denominator in the rational function. It works the best if we can show that for a particular example here. In this case, the denominator is multiplication of a number of factors. And the numerator, we keep as just any polynomial that has less degree than the denominator. And here is the correct decomposition setup. We have a over x, b over x squared, and c over x cubed. That corresponds to this x cubed term. Then we have d over x minus 1 and e over x minus 1 squared. That corresponds to the x minus 1 squared in the denominator. Then we have those two terms with a linear polynomial on the top. That corresponds to this factor in the denominator. Finally, we have these two terms that correspond to this x squared minus 4 term in the denominator. If you count all those parameters, the number of the parameters a, b, c, d, e, f, g, h, I, j, k, the total number of parameters is 11. It is the same as the degree of the denominator, which is also 11. Is this just a coincidence? We are going to show that they must be this way. It's not a coincidence. Let's recap what we just did. In the decomposition, we are only allowed to include two types of terms. The first one is the linear factors and its powers. We should use constant numerator for all those terms. And those are a, b, c, a over x, b over x squared, and c over x cubed. Those are for the 1 over x term. And for x minus 1 squared in the denominator, we have d over x minus 1 and e over x minus 1 squared. For this x squared minus 4, we first break it into x plus 2 times x minus 2. Then we treat it as two linear terms with constant j and k on the top. The second is the irreducible quadratic factor and its power. By irreducible, we mean for this x squared plus 2, you cannot further break it down into linear factors because this quadratic has no real zeros. And for this irreducible quadratic factor, we should use linear numerator. That's fx plus g and hx plus I. So the essential difference between 1 and 2 is that in the first case, it is the power of a linear factor, while in the second case, it is the power of irreducible quadratic factor. They are essentially different. This process was best described by this page, so you better read it carefully and read at least 3 times. It has everything you need to know. In the following, we are going to show that why the degree of the denominator must equal to the number of the total parameters in the decomposition. First, we must notice that the same setup template must work for any numerator polynomial that degree is less than 11. So we set up the numerator as 10th order polynomials with 11 coefficients that from A0 all the way to the 10th power coefficients, A10. Second, we notice that the summation of the decomposed terms, that's all the terms on the right hand side, actually generates a numerator of degree 10 as well. So we can write this polynomial as m of x equals a 10th power polynomial with all the coefficients here, the first, second, 10th, and 11. And each of the coefficients here, we use this box to represent that there are different expressions of the coefficients a, b, c, d, e, f, g, h, I, j, k. How it works is that we are going to let m x equals n of x That is, we are matching 11 coefficients for them. We will have 11 equations for 11 unknowns. That is 11 parameters. That means we are going to have a unique solution for those parameters we set up. So far, we have shown that the number of parameters in the decomposition must be the same as the degree of the denominator. So to ensure the unique solution for those parameters, we put this as a requirement. It's required that the number of ABCs in the partial fraction decomposition must equal the degree of the denominator. And this is very clear for this example. You have x cubed term, so that's where you have 3 parameters for this term, a, b, c, and then you have the x minus 1 square. That brings you 2 parameters, that is d and e, in the decomposition. Then you have the irreducible quadratic term with the multiplicity of 2. That will bring 4 parameters, f, g in the first one, then h and I in the second one. Finally, you have x squared minus 4, but that can be broken down into x plus 2 and x minus 2. That will bring in 2 parameters, j and k, in the decomposition. As you sum the number of the parameters, indeed you verify that it's 11, and that is the degree of the denominator, d of x. In this page, I'm trying to explain to you why some of the terms should not be included in the decomposition. First, we should not include those terms, because a term like this can be further split into 1 over x minus 1 and 1 over x minus 1 squared terms. So that means it should already be captured by those terms already. For example, x plus 1 over x minus 1 squared can be split into 1 over x minus 1 plus 2 over x minus 1 squared. And they should be included in those terms. And for the same reason, we should not include those terms, ax plus b over x cubed. That's because a term like this can also be split into terms of x squared and x cubed, and those should be already captured by those terms that in the decomposition. And finally, we should not have this term in the decomposition because x minus 4 is reducible, and it should be factorized into x plus 2 times x minus 2 and be further split into 2 linear terms like this. And here are more examples show you how you correctly set up the partial fraction decomposition. It's all about what's on the denominator. So in those examples, I could simply put the numerator equals 1 because this template set up here should work for any numerator in the input. And I ask you to take a close look at all those examples shown here. And for each one of those, you should be able to verify that the number of parameters in the setup should equal, all of them should equal to the degree of the polynomials in the denominator. Finally, I want to take this opportunity to show you a trick to quickly solve some of the simple questions in partial fraction decompositions. In this example, we want to do decomposition of this rational function. So we set it up as 2 terms, a over x minus 3 and b over x minus 4. Then you sum them by having the common denominator. Then you compare the numerator on both sides. Notice that this equation must hold for any x. So that means we can use specific value of x to get the value for a and b. That's how it works. For example, we can let x equals 4. So that way, you plug in x equals 4, you have 4 on the left hand side. Then you have a times 0 and b times 4 minus 3 on the right hand side. So that would immediately give you b equals 4. At the same time, we can let x equal 3. We plug in x equal 3. Then you have 3 on the left hand side. And the right hand side, you have a times 3 minus 4. That is 1. Plus b times 3 minus 3, that is 0. You immediately get minus a equals 3 then a equals minus 3. This way, you solve for a and b without actually forming a linear equation for a and b. So it's a bit faster than what we did before. You must understand that the underlying principle of this method versus what we used before was the same. That is based on the fact that those two polynomials must be the same. That means the equation must hold for all the x. And here's another example. You can use this trick to simplify a little bit the calculation. The partial fraction decomposition of these rational functions, x over 1 plus x, x squared minus x plus 1, that's a decomposition of 1 plus x cubed. You set up 3 parameters. Then you can sum what's on the right-hand side. What's on the right-hand side? You will get this numerator and this denominator. Next, you compare the numerator from the left and from the right. You will get this equation. This is the equation. Now we can form the equations for a, b, and c without actually expanding those terms for the polynomial. Let's see how it works. If we let x equal 0 in this equation, right? If we let x equal 0, you will have 0 equals, you plug in 0 on both left and right, and the equation, you have 0 equals a plus c. Then you plug in x equals 1, you will have 1 equals a plus b plus c times 2 on the right. You plug in x equals minus 1, you will have minus 1 equals 3a. So we can immediately get a should equal to minus 1/3. Then you plug in this into the first equation, you get c equals 1/3. Then you plug in that to the b. You can plug in a and c into the second equation, you will get b equals 1/3. That solves all the parameters a, b, c without the need to expand the polynomials.